In this bag is a piece of testing equipment so sophisticated and so expensive that for its cost, I could literally hire a full-time butler. It has an arbitrary waveform generator, power analysis options, automotive protocol. Okay, to explain what the crap it is, we've got Lucas from the lab who's using it for our power supply testing processes and who can hopefully explain a little bit of what we're about to look at. All I know is that this is the Rohde & Schwarz
MXO 58, 2 gigahertz, 8 analog channels, 16 digital channels, good oscilloscope.
The funny part is if you break it down, an oscilloscope doesn't really do that much. Just like your multimeter at home, it measures voltage using probes, but what makes it special is the fact that it can show that voltage and changes in voltage over time, with this particular one being able to handle, 4.5 million signals per second? That's a lot, right?
That's a lot, yeah. Waveforms.
First, I want to have a look at the accessories.
Sure, yeah.
And I'll try not to break anything.
Okay.
That's why he's here. Why don't you explain some of these probes to us?
Sure, yeah. So it comes with 8 analog probes. These ones here, I believe they're 10-to-1 probes.
Would you abbreviate that like ANAL for the analog ones as opposed to like digi, you might say digi probes or like anal probes?
No.
So what do we use these ones for?
So this will just be your general probes for viewing any waveform really.
Right.
But it gets the full bandwidth, and we have digital probes as well, but those will just be 1 or 0. This gets whatever voltage is.
Now this is pretty overkill for what we use it for, is that correct?
Yeah, this is a lot for what we do. We just measure the 4 or 5 rails on a power supply and some inputs to it.
Conceivably, could we use this to look at something like memory signaling, or is that too fast?
That's probably too fast. There's fancier oscilloscopes for that, but we have used this for some LTT projects like the Soviet keyboard.
Oh, when we were trying to reverse engineer it.
Yeah. Ariel and I worked on that pretty closely and worked to see what all the signals were saying and decode it, so that was pretty cool.
That's super cool. There's a little more to these than just the probes themselves. I noticed these little color coding rings and whatever it is that you're putting back in that baggie.
Yeah, so the color coding is just helpful for color coding. This is a typical, flying lead ground cable, so obviously you need to complete the circuit.
Yeah.
It's got a little wrench in here for controlling the capacitance of the cables.
Why do I want to change the capacitance of my probe?
To compensate for the inductance of the probe. So because it's a wire, all wires have capacitance and inductance.
Oh.
Yeah, it's hard to explain, but square waveform, it's you want it to be exactly square, but any inductance or capacitance will skew that. So because it takes time for voltage to change and rise. So you can compensate for that by adjusting the capacitance typically.
Is that it for the accessories? Basically, it's just got lots of probes in it?
It's got some VESA mounts too.
Oh, okay.
So you can mount it on
a monitor.
Yeah, you can get an arm for your rack too to hang it off.
Okay, cool. And then other than that,
manual, power cord.
Let's have a look at the scope itself, and maybe you can show us some of the wizardry you do with it. Let's see how much of this I can figure out on my own. Oh, fuse, power, on-off switch. I got that far. Whoa, it has an SSD?
I guess. I've never opened that.
Remove. What?
I don't know.
What? What are you worried about?
Never tried it.
Well, it's first time for everything. Oh, cool, it's just an M.2 drive. I want to open it. What M.2 drive would Rohde & Schwarz trust for their oscilloscope? Oh, look at that! It's our many-time sponsor, Kioxia.
Nice.
It's actually more important than you would think to choose a high-quality drive for an application like this, because I would think it would just be constantly overwriting. Or I guess a lot of it would actually go straight to RAM.
In memory, probably, yeah.
And then only be output to the SSD under, this is only 256 gigs.
Yeah, one of their advertising features is they have a ton of memory, so they can store all those waveforms for a long history and a long sample rate, or fast sample rate.
And we have extra options on ours, I believe, that expands the memory, is that correct?
Yeah, I believe, yeah.
All right, so, I forget how this goes together now. That may have been a tactical error.
There are way faster oscilloscopes. I was talking to the guy we know at Rohde & Schwarz, and he's like, yeah, it's a good, standard lab oscilloscope, but there's definitely faster ones and more expensive ones. They go into like dozens of gigahertz and faster for communications and all that stuff.
And do we have any idea what something like that would cost?
Hundreds of thousands, probably.
Cool.
Very, very specialized.
So this is like really fancy to us. And then we've got people who work at, you know, NASA or whatever that are like, aw,
Yeah.
cute. Okay, let's try and put this SSD back in. Uh-oh. I know, Lucas, I'm trying to fix it, okay, man? You seem stressed.
Hopefully it works.
Look, it just says do not remove during operation.
Okay.
It doesn't say, did you think it just said do not remove? Did you not
I
get a
didn't
look
read
at
it. I didn't read it.
All right, cool. What else are we looking at here? Well, obviously, we've got rubber feet that allow it to be in, I don't know, other orientations. They go all the way back. We've got a couple of 120. Jeez, this thing needs a lot of cooling. Is that just the processing needed for this level of sampling or what?
It's doing a lot of compute. It does dissipate a little bit of power inside as well, depending on what you're like probing.
Oh, I see.
Like not on purpose. Obviously, they would love to not take any power, but you know, in measuring, you have to take in a little bit of current or whatever. So
that makes sense. And then, oh, here we go.
So trigger in, that'll be if you want to have an external trigger to capture something specific. Like if you can't manage it in the software.
Right. I'm good.
And you want to capture something.
Or if it's like something that happens unpredictably or it's too fast for you to like manually go, oh yeah, I want to capture now.
It's all too fast to manually capture now,
Right.
but you know, it'll happen automatically. And then Gen 1 and Gen 2, never use those, but I believe those are just from the function generator, the arbitrary waveform. Ref out 10 megahertz. I think that's also the function generator. This one probably calibrate off of, I'm not sure. Trigger out is for when you trigger on something like one of the waveforms, then you can send a pulse out of there.
Got it. And
then
USB device.
I'm not sure what that one's for.
Well, it's a target port, so I guess if we wanted to hook it up to the computer via USB.
That's possible.
Meanwhile, on the other side, we can connect USB devices to it. Do we connect it to the network, I guess, for
Yeah, we do. Yeah, for
control?
all of our control and for viewing.
And then do you use the HDMI and DisplayPort out, or do you just use the built-in display?
No, you can do it all over LAN. Like you can display from the computer.
So you use LAN both for remote control of the unit and to output to a display.
Yeah, it's just for the same thing. But actually, I was looking on the website today, and they have headless units of this as well. So it's basically the exact same thing, but without the screen. And you can just use the display out or the LAN.
Okay, but this one has a screen.
This one does have a screen.
Okay. Do you use the screen at all, or is it just kind of superfluous?
Yeah, I mostly use the screen. Use the LAN just for monitoring if I'm, at my other desk.
Got it. So there's your 8 analogs, and then I guess each of these does 8 digital channels.
Yes, that's correct, yeah.
Oh my God, why does it have so many USB ports on it?
We use it to save waveforms to USB if you want, or you can use it for some power.
Can you run us through some of these controls here?
Yeah, so a lot of them are multi-use and they'll do different things depending on the screen, and it's a big touch screen, so you can do a lot with that. But you can control each of the 8 channels plus any logic ones and math ones, control the vertical scale and position to move waveforms up and down.
Makes it a little easier to see what you're looking at, I guess.
Yeah, I guess if you want to change view or see a certain section of something.
Sure.
You have horizontal controls for horizontal scale or position.
Why don't we plug it into something
Move
and then
back and
maybe you
forth.
can show us this in real time then?
Yeah.
Okay, yeah, let's do that. When it comes to this kind of stuff, they just kind of say, here's the one I want. And I go, is it a good one? And they say, yep. Do you have like a power supply? Is that what we're gonna look at? Or like, what are we gonna look at?
Oh yeah, well, do you want to start the screen recording?
Oh yeah, and tell you about our sponsor.
Thanks to Motion Gray for sponsoring this video. Their Ergo 2 is one of the most affordable options for sit-to-stand desks on the market, making your next work or gaming station upgrade even cheaper. It has a weight capacity of 176 pounds and a height adjustment range of 28 to 46 inches, powered by a silent but powerful electric motor. The whole setup even ships out in one box with all the tools you need for assembly included. Pick one up with our link for an exclusive 15% off on top of any discount they may already have.
Hey, it's booted up. Now what?
I had a little demo prepared.
Ooh, a demo. Demolition?
No, demonstration.
Okay, so we got a little SBC of some sort. What's that?
Like an ESP32 I set up here, and I've just programmed it to send a little command here.
Okay.
So one of the neat things about this oscilloscope is that it can do a lot of decoding of digital signals.
Oh, so we tell it which pins to monitor out of our 8 channels here.
Yes, sorry. So I plugged in the digital.
This is
digital
again,
probe.
This is the thing about engineering people. They just start doing stuff assuming that everyone around them is like following along. Yes, carry on.
So I've plugged in the digital probe here, channel 0 and 1. And I can go in here and go into the apps and protocol and to SPI. So I'm communicating over SPI.
Okay.
And set this S clock on channel 1, I believe it.
So is this the kind of thing where if you didn't know how this was outputting, it would be a bunch of trial and error to figure out how to even monitor it? Like if you were
Yeah.
trying to reverse engineer something?
Yeah, so a lot of it's like a lot of the setup, it's done while you're testing. You know some of these parameters. We also have to just kind of find some of this. I have to also change the trigger so that it triggers onto that one. So there's plenty of nice triggers in here, but we're just triggering off of a digital signal
Okay.
and the edge. So whenever it rises, then it will capture a waveform. And that's how we can see this here.
Okay. And what are we looking at here?
So here, it's got automatic decoding of this. So
Okay.
we just capture a single waveform. You can just capture a single one instead of run stop as it was before, capturing all the latest ones. You can see, and it's just automatically decoding the message I was sending.
Oh, look at that. It says PSU circuit,
Yes.
which is the channel where you guys can see all of the power supply testing that Lucas does.
What are the chances? A more practical case would be you have your PCB or some other device.
Did you just make this be a keyboard, essentially?
I guess in a really slow way, yes, we can make it just a keyboard, yeah.
Could you just type into
not
it?
as
And
cool.
could it detect that as well? If you set up your triggers so that it...
Yeah, and like decoding of whatever communication standard you're using, yeah. It's got a lot of different ones you can do, like CAN bus and other things for more automotive.
for like automotive.
Yeah, exactly.
Okay, that's pretty
and more
cool.
complicated stuff. So this is like a really simple example, but if you want to see if your sensor was actually giving back the proper values, there's maybe a breakdown in your line somewhere, you could monitor that and see, oh yeah, it is sending everything back correctly, just we're losing it or we're decoding it incorrectly on our own.
Oh, that's super cool for diagnostics then.
Yeah, exactly. And this is only using 2 of the 16 channels. So if you had like a hugely parallel bus, then you could decode them all. Somewhere like this would be awful to, you know, count on your own and see 1001 kind of thing.
Right. Because this is each of our characters here.
Yeah. Yeah, it's also a touchscreen.
Right. Yep, you mentioned that. So we're back to our first signal here. This is a capital P. On the bottom, we have just our clock that tells us when to sample a 0 or 1. And then on the top, we've got our signal. So what we're looking at here then is our first clock telling us to sample, that's a 0. Then on our second sampling point, that's a 1. On our third, it's a 0. On our fourth, it's a 1. And for the last 4, it's all zeros. So this one would be 0101 0000, and that's a capital P in ASCII then.
Yep.
So then this would be how you guys reverse engineered that keyboard then.
Yeah, a lot of that, we hook it up and see like when things are high and low, and trying to figure out what all those random pins were, because there were a couple we weren't even sure what they were. And I think that's how we found out that one of the decoding chips was broken, and it was just sending all zeros. Like so, it's sending the same kind of bits, but then the second 4 bits was always 0 for all of them.
Right. I remember that. The first half of each byte was working, and then the second half of each byte was broken.
Yeah,
and all
because
zeros.
the chip was dead, and so we could see that.
All right, enough of the high school electronics class demo. Let's get this hooked up to a power supply and show you guys how we actually use it. So these probes are all just like wired into our testing equipment,
Yeah,
right?
sorry, it's not, you can't see it, but these run into the test chamber.
Okay.
Connected to connection board, which is connected to the power supply.
Here, I can show you guys what he's got in there. Here's our second one. Ah! So all his probes are going into this and monitoring our various voltages from the power supply. And what's really cool is Lucas painstakingly soldered our measuring points to the bottom of our PCB so that we don't have to worry about this cable length affecting our measurements. What are we looking at?
So another great part about this oscilloscope is the automatability of it. So we're able to do a lot of our tests without actually touching a lot of it. We just have to set up all the programming beforehand, and then as it's testing, it'll send all the commands to properly configure it. And test without us having to stand here.
Well, we really like standing here, don't we?
We love it, yeah. And hopefully this will work. I don't know, somebody removed the SSD, so.
What? It's probably fine. Oh, should we talk about some of the things that ours is optioned with?
Oh, sure, yeah.
It has a 1 gigabit GPTS memory extension.
Yeah, so that's 1 gigapoints memory extension. So that's another one that lets you capture a lot more waveforms, and it's a lot of memory, like we said before.
Oh, for longer
RAM.
waveforms.
Yeah.
Okay.
And more of the same. So if you're measuring if we're measuring that thing, it was saying PSU circuit,
Yeah.
that was repeating like once a second or whatever.
Right.
And so that allows us to capture like multiple samples of it, and you could average them or see if there's any like aberrations.
Right. So for diagnosis of, say, for example, like an an erratic error that only shows up once in a while, that could be really useful then.
Yeah, exactly. This is great for that, and a lot of oscilloscope is used for that, where like 99% of your signals will be exact right waveform, but you want to capture the 1 or 2 that isn't.
The intermittent
like
problem.
they call them like runts or whatever. Yeah, or it's like maybe it stayed high for too long, or there's some kind of glitch.
You know, there's a lot of people that find that word pretty offensive.
Right. This is our brownout test that we do for PSU circuits. We basically just turn off the input power to the power supply for a very short period and see if the power supply survives. So you can see here, it's doing a lot of stuff on its own. It basically just configured itself so that it's got all the right measurements set up.
Cool.
And it'll capture this waveform afterwards. So
okay.
There we see here.
So what we're looking at here then is AC power doing its thing, right? And then we're looking at whoopsie doodles, no AC power, but our 12 volt on the power supply was uninterrupted. And what's our purple one here?
So yes, this is
3.3 volt.
3.3 volt.
Derp.
There's 5 volt and the power good signal. So that's the one from the power supply that's telling the motherboard and the computer, like, power is still good. I can still guarantee that we have the right output voltages.
What if we gave it a longer brownout then?
Exactly. We'll proceed through this. It'll go through and it saves the waveforms. This is how we save them back to a file, and we can later graph those and create large graphics from them.
And eventually that power good signal is going to be like, no.
Yes, yeah, but hopefully we'll capture this. You know, it's always a lottery. We're doing it live. So we can see here, it's in blue, so it's hard to see. But you see it cut out here and went low for a while and came back up. So for that short period, the power supply was saying, you know, I can't guarantee 12 volts output.
And if we have a good motherboard that behaves the way that it should say, hey, I don't have good power.
That'll shut down the computer, yeah. So at that point, it's like, it's nice that it's kept the other voltages high, but it's already turning off your computer because presumably that's enough for it.
And this is exactly the behavior we'd want. We would want it to say, hey, the power's not good before there's a major interruption to the voltage it's delivering to our components, because otherwise, I mean, this is a very, very small surge, but if we had a bigger surge, that could be an issue, right?
Surge and just reliable things. So it may be trying to save memory to storage or something, and it might corrupt that or have some unpredictable effects. We'll see if we'll get one where it just fully drops out. But you can see there's already little dips in the voltage.
Right. Oh, okay. So it really didn't like 25 milliseconds of power being gone?
About 22 milliseconds or 24. I'm not sure exactly which one. But yeah, you can see there's blips in the 12 volt and it just completely drops out. But the power good line dropped before that.
Now, a lot of our testing is focused on the ATX specification and making sure that power supplies adhere to it. Have you encountered any that do not meet the ATX specification?
Yeah, a lot of the power supplies will not quite meet in some places, like, oh, maybe it's in the dynamic tests, it doesn't quite meet the voltage regulations, or one of the timing's off. But a lot of them, it's not a huge deal. And it could be a part of how our test setup is different from the ATX.
Got it. So is that why we don't necessarily publish every result that we record right now? Because we're kind of waiting to make sure that it's on the up and up?
That we're confident in it. And we don't make any claims of like full ATX certification with that. So yeah, it's just, you know, indicative.
And one of the things that we really care about a lot, though, and that we are publishing now, is any failures in safety mechanisms that are built into power supplies. Because, you know, I don't think that most people are going to look at a slight blip in the 12 volt rail when they have a 15 millisecond power outage and go, ooh, I'm not going to buy that power supply. But we've had some that will just outright fail under an overcurrent scenario where we are drawing more power than the power supply expects.
Yeah.
Which we don't expect it to be able to provide more power than it's rated for, but we do expect it not to catastrophically die.
We have had a couple die during this test where we're just shutting off for brief periods of time. Can't explain those ones, but because it's not super onerous. But
yeah, like this is something that a power supply should be able to handle.
Yeah, we do it a lot of times, and we do it at 0 degrees, 20 degrees, and 40 degrees. But it should be, you know, fairly survivable, I think.
Do you have any more tests for us to look at?
Yeah, we also have the timing test that we use the oscilloscope for, and I think that's, you know, more interesting than the brownout one.
When you say timing, what do we want to know? How does the timing matter of a power supply? I mean, it's DC. There's no signaling. There's no waveforms even. There
is signaling, so there's a couple of signal channels on that, like the power good and the power on. But there's a specific time they have for how long it takes for the voltage to rise to a certain level or to drop, or delays between those. So this configures the oscilloscope for a turn on waveform. which we get here.
So do we want to go from 0 to 12 volts really quickly, or do we want it to be slow? What do we want?
I believe there is a maximum time. I don't know the exact time now, but the maximum time for 0 to 90% of the voltage spec, so of 12 volts, 5 volts, and 3.3 volts.
Got it.
And then there is also a spec for the delay between them going high and the power good signal going high. It'll save this waveform and then reconfigure so that it can save the turn off waveform, which is also important for like brownout and stuff. And so this one, the first one, will be basically just flat lines once it's saved, because there's very little load on the power supply.
Yeah.
But future ones do actually drop, and you can see them there.
It takes about 2 days to fully test a power supply, and if we have a failure, we always obtain another unit and fully test that additional unit to see if it was just a one-off bad unit. What's interesting to me though is so far, we haven't had a lot of bad units that weren't just a bad power supply. All but I believe one of the ones that have failed, the second unit has failed as well.
Yeah, there's one or two that the first one failed and the second one survived, but so far it's been, yeah, they both die, and often around similar tests. So here's another one. So this is trying to turn on with a load, and obviously it failed that. A lot of power supplies do. Even though I think it's in the spec, the ATX spec, that it has to be able to turn on with a load, they just can't because, you know, it's not typical, I guess. Your GPIO isn't pulling power before it has, you know, a voltage.
We can also use this for ripple testing of a power supply, is that correct?
Yes, yeah, we do that same
Can
thing.
you explain, like on 5, why ripple matters?
Because a perfect DC voltage output, like 12 volts, it'll be perfectly flat. But because we're in the real world, there's capacitance, inductance, loads, everything else, it's not going to be flat.
Yeah.
There's some ripple to that.
And we can see that. We can
yeah,
see
you
it
can
right
see a little bit of noise in there.
in the line there. Why does excessive ripple matter?
Because the components later in your computer are expecting a really constant supply and something they can predict and, you know, operate consistently on. And they've further regulated it down to other voltages like CPU, like 1.2 volts and stuff.
Yeah.
But even those regulators want a really consistent input voltage.
Got it. So it just helps with general stability and reliability. Could it improve longevity to have low ripple?
Yeah, it'll put less load on the capacitors over time, put less energy in and out of them. Here I have another waveform where this one actually went down. So this is another one. So during the timing test, we can measure how long it is between the power, like it turning off, and the power supply shutting down, and how long it takes for each of the voltages to drop. This one's at like a 10% or 20% load.
So this is the whole thing where you hit the power switch on something and it takes a minute for it to like...
For the LEDs to, you know,
Yeah,
exactly.
okay.
So that'd be like for a small load. And you'll see with like even larger loads, it's almost instantaneous, the voltage drops.
Oh, one more thing actually. We've alluded to it, but I don't think we've explicitly said what one of these run-of-the-mill benchtop oscilloscopes is worth.
It's a bit of a range depending on options, but it's about 20K to 50K US dollars.
Right?
Yeah, go out and buy one, you know.
Yeah.
Use our affiliate code.
Lucas from the lab, everyone, and the Roden Swartz MXO 5 series. Subscribe to ShortCircuit. And Power Supply Circuit, for the love of God, subscribe to Power Supply Circuit so you can learn more about power supplies.